Hey everyone, I'm going to go through the 4 slides in that 3.2 arc length and sector area notes day 2. So I encourage you to follow along in your notes and pause this video, take some notes as you need to. Like I said, I'm going to go through the warm-up and the other 3 slides. It's just an extension of what we talked about yesterday with arc length and area of sector, so but for some problems that are a little bit more involved. So for the warm-up, again, it's a second hand. We know that the second hand, the second hand does 1 revolution every 60 seconds. So they want to know how far will the tip of the hand travel in 54 seconds. So it's asking us for an arc length, and they're giving us a radius of 12 centimeters. So we simply have to take this 1 revolution every 60 seconds and turn that into an angle, knowing that it's going to travel for 54 seconds. A couple of different ways to do that. One way is we know 1 revolution every 60 seconds can be changed into radians because we know 1 revolution is 2 pi radians. That gives us pi over 30 radians per second. If this is going to be happening for 54 seconds, 54 times pi over 30 is going to give us 27 pi over 15 if we divide each by 2, and if we divide by 3, that gives us 9 pi over 5. That's going to be our theta. In 54 seconds, the second hand will go through 9 pi over 5 radians. So we'll do the 9 pi over 5 for theta times our radius of 12, multiply them together, and that gives us, let's see here, 9, gives us 105 pi over 8, which as an approximation would be 67.85, and that's going to be centimeters. We're looking at a distance. If we want to look at 21 minutes, we know again the second hand makes 1 revolution every 60 seconds or every 1 minute. And we know 1 revolution is 2 pi radians. We do that for 21 minutes. That's going to give us 42 pi radians. So for the second part, we have an angle of 42 pi. Our radius is still 12. Multiply them together, we get 504 pi. And again, that would be centimeters. That's for the warm-up. Again, S equals theta times R. Just find your theta by using what you know a second hand does. For the next example, rope attached to a weight is being wrapped around a drum. They want to know the height the weight is raised. Well, the height the weight is raised is going to be the same as the arc length. So we're asking for arc length, or the height the weight is raised. It's the same thing as arc length. So they tell us that the radius here is 8 inches. They tell us the drum is rotated 40 revolutions. So our theta is going to be 40 revolutions. We know to change from revolutions to radians, multiply by 2 pi. So our theta is going to be 80 pi radians. And once we have that, it's just S equals theta times R. 80 pi is our theta. Our radius is 8. That gives us 640 pi. Again, that's going to be inches. If you want a decimal approximation, 640 pi in the calculator would be 2010.62 inches. So pretty straightforward here. It's just recognizing that the height that the weight is raised is the same thing as how far a point on a wheel is going to rotate around the wheel, so arc length. The third and fourth examples are pretty similar. The key with these, when you have two gears attached by a chain or two gears that are meshing together, the idea here is that the arc length at the small gear is going to be the same as the arc length at the big gear. The reason for that, as some point rotates around the small gear, let's say it goes, just making up a number here, 6 inches, then some point on the chain is also going to move 6 inches, which means some point on this wheel is also going to move 6 inches. So the key here is that the arc length of the small wheel or gear is equal to the arc length of the big wheel or gear. So I find the easiest way to do these is set up two columns, one for small, one for big, and start at whichever one, the small or the big, they give you information for, or all the information for. So they tell us the radius of the small gear is 8 inches, and the radius of the big gear is 18 inches. It says the small gear rotates through 6.25 revolutions. They want to know how many degrees does a larger gear rotate. So we're looking for theta here in degrees. So it's basically doing two arc length problems, one for the small gear, taking the arc length of the small gear, taking that information over to the big gear, and solving for theta. So let me just go through that. So we have S equals theta times R. Remember, theta has to be in radians first. So we're going to take our 6.25 revolutions, multiply that by 2 pi. That's going to give us 12.5 pi radians. Again, remember, revolutions times 2 pi will give you radians. So we have 12.5 pi for our theta. Our radius is 8. 12.5 times 8 is 100. So you have 100 pi, and that would be inches for the small gear. So some point on that small gear is going to go through 100 pi inches when that small gear rotates 6.25 revolutions, which means the big gear is also, or some point on the big gear, is also going to go through 100 pi inches. So we're just going to do another arc length problem for this one. We have our S and we have our R. We're looking for theta. So 100 pi is our arc length. Our radius is 18. Do 100 pi divided by 18. That's going to give us 50 pi over 9. You can use a decimal if you want to. That's going to be 50 pi over 9 radians. Remember, this formula only works if theta is in radians. So whatever you put in, the formula is going to assume is radians. Whatever comes out, the formula is going to give you radians. The question is asking for theta in degrees. So last step is to change that number of radians into degrees. So 50 pi over 9 radians. We know to change from radians to degrees, we're going to multiply by 100 over pi. You see the pi's will cancel. I know 180 over 9 is going to be 20 over 1. 50 times 20 is going to be 1,000 degrees. So again, the key there is that arc length for the one small gear is the same as the arc length for the big gear. So whatever you find for arc length for the small, that is arc length for the big, and it's how you kind of connect the two pieces. Okay, very similar idea, or exact same idea, I should say, for the second example. Okay, just a little bit different setup. Attached by a chain, larger gear drives a smaller gear. Again, we'll set up the two columns, one for small, one for big. They give us a radius of a small gear in the figure is 12 inches. The big gear, the radius they give us is 28 inches. And it says a larger gear rotates 6 revolutions. So that's our theta for the bigger gear. So in this case, we're going to start with the bigger gear. Then we're going to know how many revolutions does a smaller one rotate. So we're going to start with a big and then work our way over to the small. Again, make sure your theta's in radians. So 6 pi, or 6 revolutions times 2 pi, is going to give us 12 pi radians. So then our arc length is going to be 12 pi radians times a radius of 28. 12 pi times 28 gives us 336 pi. That's an arc length. That's going to be measured in inches. Keep in mind the units we multiplied there. If you look at just the units, we did 12 pi radians times 28 inches. Remember, radians has no unit, so we're going to end up with just inches. Once we have that arc length, that's the arc length for the small gear also. So we have 336 pi inches. The radius for the small gear is already in inches, so our units match up. So just plug and chug into S equals theta times R. 336 pi is equal to theta. We have a radius of 12. Divide both sides by 12. We end up with 28 pi. Again, that's going to be radians. This formula only works with radians. And we want to change that into the question asking how many revolutions does a smaller rotate. So if you want to change from radians to revolutions, we're simply going to divide by 2 pi. Again, you can think of it like this if you want to, where we know 2 pi radians is 1 revolution. It essentially works out to be that you're dividing by 2 pi, and that's going to give you 14 revolutions. So again, the key with some of these problems is arc length for the small gear and the big gear, they're the same. As long as you have two things connected by a chain, sometimes you'll see them kind of meshing together, two of them mesh together. And then if you're raising something or moving something, the distance that the object is raised is the same thing as the arc length. So again, I hope this makes sense. I will be back tomorrow. We can go over any questions you might have. Once you're done with these and have those questions answered, the homework is going to be this 3.1 to 3.2 homework. Looking at numbers 1 through 12, but you're skipping number 9. So some of these are just converting from degrees to radians, radians to degrees. Some questions similar to what we looked at yesterday in terms of just straightforward problems. Find length of an arc, find the radius. How far does the tip of a minute hand travel? That's going to be an arc length. 8. Here's the two gears again, not connected by a chain, but the small gear and the big gear have the same arc length because those two gears are connected. You're skipping 9. 11's another gear problem. 10's an area of a sector problem. And 12, similar to the weight being lifted, where the distance of weight is raised is the same thing as the arc length. And that is it. Like I said, I'll be back tomorrow. If you have any questions, we can go over those questions. Take care.